This is not a house fire caught by chance. It is a full-scale room built by NIST, filled with ordinary furniture, cameras, and sensors. And this wall of flame began with one small propane flame touching a sofa pillow. The surprising part is not that the pillow burns. Watch what happens above it. A dark layer collects under the ceiling. That is the first clue. Hot smoke and combustion gases rise, spread sideways, and begin turning the ceiling into a radiant heater. At first, the fire still looks local. The sofa is burning, but the rest of the room appears separate from it. That impression is dangerously misleading. Energy is accumulating in the gas layer faster than your eyes can judge from the flames alone. The second clue is flame moving through that upper layer. Firefighters call this rollover. The hot gases themselves are burning near the ceiling. When you see it, the fire is no longer only traveling from one object to the next. Now watch the graph. NIST is measuring heat release rate, the fire's power. The line is not a temperature reading. It tells us how quickly combustion is releasing energy. As the room heats, the line accelerates. Then comes the third clue. Heat radiating down from the gas layer drives exposed surfaces toward ignition. NIST describes flashover as the transition where surfaces across a compartment ignite almost simultaneously. In this test, flashover was recorded at 6 minutes and 3 seconds. Only about 38 seconds later, the measured heat release rate peaked at 9,639 kilowatts, more than 9.6 megawatts. The room did not merely contain a larger sofa fire, it had become a different fire system, with nearly everything inside contributing fuel. This was a 3.7-meter square room with a cotton-covered sofa and no protective barrier fabric. The test eventually released 2,636 megajoules and burned an estimated 88 kilograms of fuel. Those numbers describe this experiment, not a countdown guaranteed in every home. That distinction matters. 6 minutes to flashover does not mean you have 6 minutes to escape. The U.S. Fire Administration warns that after a smoke alarm sounds, you may have less than 2 minutes to get out. A different room, ventilation path, fuel load, or open door can make the timeline faster or slower. So the useful lesson is not to memorize 6 minutes. It is to recognize the energy cascade. A small flame heats the upper layer. The upper layer radiates heat back into the room. More surfaces release fuel vapor and ignite. That feedback loop is why the final transition looks sudden, even though the room has been building toward it. The practical response must happen before those visual clues appear. Keep working smoke alarms, no 2 ways out, and leave as soon as the alarm sounds. Close doors behind you if you can do so safely. A closed door can limit the flow of heat and smoke. Once outside, stay outside and call emergency services. NIST ran this test precisely because small samples cannot reproduce all of these room-scale interactions. 5 cameras watched from different positions while instruments tracked heat and combustion gases. The white curve on the video is the measured heat release rate synchronized with the room. At the end, firefighters enter only after the experiment has produced the data researchers need. The room is expendable. The measurements are the product. They let engineers compare materials, protective barriers, detection, and fire protection using evidence instead of a guess. Replay the transformation once more. A tiny pillow flame, a descending smoke layer, fire rolling through the gases. Then the room ignites as a system. The reason this footage feels unreal is that our eyes follow the visible flame, while the real turning point is being built in the invisible heat above it. This was a real NIST experiment, not AI footage. Subscribe to Why It Spiked for more authentic footage, hidden clues, and fast answers.